Okay, so we had a little bit of technical difficulties, but hopefully this will be fixed, the new layout. Today we're going to be talking about using exponential functions as models. And we're going to start off with one of the most basic common models we see, which is using compound interest. Compound interest is given by this equation right here. And in this equation, our A is going to be equal to the total amount we get after we input some certain values, such as the P. P is the principal. It's the initial amount that we invest. Just think about it as your initial value. Our R value is going to be our annual rate of interest. So if you hear something like we have a 3% interest rate or 5% interest rate, that's that annual rate of interest. And then we have our N value, which is how many times our interest is compounded a year. So if it's compounded quarterly, that's 4 times a year, or if it's compounded monthly, 12 times, weekly, 52. You get the point, hopefully. And then T is the amount of time that's passed in years. So 10 years, 50 years, whatever the question may ask. So let's get to it. Again, with any and all examples, I highly suggest you pause it and attempt to do it for yourself if you can. So with this example here, you have $1,000 deposited into account paying 4% interest and it's compounded quarterly. So we want to find the amount in the account after 10 years with no withdrawals, meaning the money is just sitting there and it's getting more money. So our P value, our initial amount is $1,000. So our A is going to be equal to 1,000 times 1 plus our rate. Our interest rate here is 4%. And again, instead of 4%, it's going to be a decimal, so it should be 0.04. And we're dividing that by the number of times it's compounded. And it's compounded quarterly, so we're dividing it by 4, because quarterly means 4. Right? And we have a total of 10 years it's happening, so we're doing 10 times the number of times it's compounded each year, which is 4. So 10 times 4. So you have a nice, big, complicated equation. We don't really have to do a whole lot of work, just kind of plug and chug in our calculator. So you could simplify it a little bit if you wanted to before you plugged it in, or I'm going to simplify it as I plug it in to save some time. And don't be intimidated by this calculator. It's just a different version. You're going to use it a little bit in calculus. And hopefully just me using it in the videos will help you pick up some proficiency with it. So I'm just going to plug in my equation that I have now. I have 1,000. Well, menu. On home calculator. All right, there we go. 1,000 times, and then we have parentheses here. 1,000 times 1 plus 0.04 divided by 4. And then we're raising this up to the 40th power because it's 10 times 4. So we're raising this up to the 40th power. Again, all we did is we took this information here, we're plugging it into the calculator. It might be a little bit hard to see, but it is there. And this gives us a final answer here of $1,488. So after 10 years of just nothing's happening with my money, I have $1,488, and I didn't see the cents there, 86 cents. And 86 cents. So that should be your final answer. And then it says how much interest is earned over the 10-year period. So how much interest is earned? Well, we're starting off with the $1,000, and then we made $1,488. So all we have to do is a simple subtraction problem: 1,488.86 minus 1,000, which gives us our final answer quickly of just 488.86. All right, moving on. Our next example: Taylor Simmons must pay a lump sum of $6,000 in 5 years. What amount deposited today at 3.1% interest compounded annually? So that means our N value is going to be equal to 1 because it's just compounded once. Will grow to $6,000 in 5 years. Again, pause, please. Attempt the problem. Attempt both problems actually, and then resume and get back to it. So we're trying to find the amount deposited. So that's our. We know what we want. We want it to equal $6,000. And we don't know what we're going to initially deposit, so that's going to be your variable P. It's going to be 1 plus 3.1% is going to be 0.031. And we're dividing that by 1. So we could write it here, but we don't necessarily need to. Right? So we can just leave it as plus 0.031. and we're raising that to 5 years times the number of times it's compounded, which is just, again, 1. So it's just 5 times 1. So if you look, this is going to be a pretty, hopefully, simplistic problem. We're just going to simplify what's here, and we're going to have that times p. So we're going to have 6,000 equals, let's bring out a handy-dandy calculator. We're going to do 1 point, and this is just easy, 0.031 raised up to the 5th power. So we're raising that up to the 5th power. Let me just bring this back into the screen. And that's going to give us our final answer. Well, not our final answer, but it's going to give us an answer here of 1.1. I didn't do a good job of remember that. 165. So let's take it to 3 decimal places here. P. And then all you need to do is just kind of divide. So we're dividing 1.165 on both sides just to figure out the answer, which here is going to give us a whopping total of 6,000 divided by 1.645. Nope, that was wrong. I have a delete key here. 165. That's equal to $5,150. $5,150.20. So that's how much money she needs to deposit in order to get that $6,000 mark. All right. We're kind of running a little long on time, so I'm going to kind of try to condense this, maybe go a little bit quicker, just kind of show you out the algebra. If only $5,000 is available to deposit now, what annual interest rate is necessary for the money to increase that $6,000? So we're assuming here that she still has, this is the only thing that's changing, and she's still compounding it annually. So in this case, we're doing, and we know our P value is going to be 5,000. So we plug in 5,000 for P. 5,000 times 1 plus R. We don't know what R is, and we're raising that to 5 years times 1, which is just 5 right here. All right, so now this is equal to, we're still trying to get to 6,000. Excuse me, that wasn't well planned. And we just need to solve for R. Well, to solve for R, the first thing we should do is just isolate this kind of exponential piece here. So to isolate this exponential piece, we can just divide 5,000 on each side. And I'm going to kind of keep this as fractions to help us out. So this cancels, and then these 3 zeros and these 3 zeros cancel. We have 6/5 is equal to 1 plus R to the 5th power. Well, how do we get rid of that 5th power? We can use our handy-dandy calculator and take the 5th root. So if we're taking the 5th root, and I'm not actually positive how to take the 5th root with this calculator, so I'm going to switch over to a TI-84 just for time's sake. And I'm going to do it on my TI-84, which is I'm just going to go to math, or I have to type 5 first, and then hit math, and then go down to 5, and then we're going to do the 5th root of 6/5, which is going to be equal to, then also we're doing is the 5th root of both sides. So 1 plus R is equal to 1.037. And now, obviously, we could subtract 1 from both sides, and we can see that R is equal to 0.037, which is equivalently, just 3.7% interest is what you would need. All right. We probably don't have enough time to explain E, but here is a formula where if we're just compounding it, if our interest rate is 100% and we're compounding it for 1 year, and we're applying it for 1 year, the number of times we compound it will grow. So if we're compounding it once a year, twice a year, 5 times a year, you can see that it's getting closer and closer and closer to some number. And this number that's getting closer and closer and closer to is actually E. So it's kind of really cool. We can probably spend some more time in class talking about this. Which brings us to continuous compounding. So because this approaches some number, it doesn't matter. It gets to a point where it doesn't matter how many times you're compounding it, because if you just, it won't ever go past E. So if we have this formula, our total amount is going to be equal to our principal, or initial amount invested, times E raised up to the rate of interest times just the amount of time that has passed. So suppose $5,000 is deposited into an account paying 3% interest compounded continuously for 5 years. Find the total amount on deposit at the end of 5 years. So we're trying to find the amount A after $5,000 has been deposited in. And it's being it's being compounded continuously. So we can use that e to the RT equation. And our rate in this case is 0.03. We're doing it. Again, our time is 5 years. So again, we're just applying this formula that we used in our previous slide. So we just take our handy dandy calculator, and we're going to do 5,000 times e to the 0.03 times 5, and will give us our final answer of, if we're compounding continuously for 5 years, we're going to make $5,809.17 as our final answer. All right, so 11 minutes in, kind of doing what we can. Exponential growth and decay. This is kind of what we're going to be getting to in this class. I wanted to get through on this video, but I'm not sure if I'm going to be able to, so I'm just going to stop the video now, and then we are going to pick up where we left off here in class. All right.